going on, guys? Welcome back. Today we are doing the second piece of the introduction to networking. This one I wanted to separate because this is where we're going to actually be doing some subnetting and actually doing breaking up the IPs and things like that, so that will take a little bit longer, and I wanted to give you guys the proper time. So let's go ahead and get into it. Before we do, go ahead and hit that like button, hit that sub button. Helps out tremendously, and it's the only way we can grow and get these things out there for people who actually need the help. So the first one is the network layer of the OSI model. I think we already covered this, but I want to cover it again just because it's part of the networking workflow. So you can see network layers, layer 3 of the OSI model, and controls the exchange of data packets, as these cannot be directly routed to the receiver and therefore blah 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 blah, right? So in short, it's responsible for logical addressing and routing. So that's where you'll see routing to other networks, right? That's the networking layer. So protocols are defined. So this is some of the protocols you're going to see in the OSI model in this network layer. It's IPv4, IPv6, IPsec, ICMP, IGMP, RIP, and OSPF. These are just examples. These are not the end all be all, right? It ensures that routing of packets from source to destination within or outside of our subnet. So basically, we have networks. We have to be able to talk to other networks. That's where the network layer comes in, right? So let's go ahead and get into the IPv4 addressing, because we can't talk to anybody if we don't have an address, right? So one thing I'm going to pull up here is I'm going to pull up a notepad, and the main reason I'm going to pull this up is because I want to show you guys the way I network. It may not be the exact same way that everybody does. I've worked with people that do it, and some people just memorize it, and that's fine. I'm not as good at memorization with math, so I write it down every time, and I'll show you what I do. So we have the IP addresses. This is IPv4. So how do we actually get assigned these things, and what do they even mean, right? We all know that an IP address is similar to a address at your house, right? It's how do I know I want to get to you? So you can see each network located, it can be identified with their MAC address, which we will talk about after the IP addresses, but the MAC address is a physical hard stamp on there. How would anyone know that, what it is, right? Well, that's where IP addresses come in, because we have what's called network address translation, and what that is basically what we have is we ran out of IPs. That's where IPv6 comes in, but we ran out of IPv4s, and the only way we would have even been able to sustain IPv4 even for a short term is to basically have what we do now, which is you actually have a public IP, and that public IP, all your router at home routes all of your traffic through that public IP. Behind your router, you have a whole other set of IPs. Those are local IPs. Those are just on your network, right? So you see that 192.168.0.1 whatever IP. Well, guess what? Everybody, when they stand up a new router at their local house or Soho, have that IP, right? Because they can use it. It's behind their router. Their router knows what it is. It's tied to their MAC address. But when they're talking to public, when they're talking to someone out there in China, someone over in Russia, someone over in wherever, when they're talking to other people across the world, they're only showing their public IP. It looks like everything's coming from one IP, and that's your public. So now we know how we get those. Let's talk about the structure. So this is where people get confused, and this is where I want to really kind of hone in on and spend the time. So firstly, the most common method of assigning IP address is IPv4 still. So I know we have IPv6, but this is the most common still currently. So this is a 32-bit binary number. What does that mean? Well, if you look, there's 32 numbers there. That's what it means. There's 32 ones or zeros. Ones or zeros. That's it. That's all binary is. Ones or zeros. This specifically translates to this. You might say, how is that possible? Whatever. Well, it's math, and we're going to get to it. So the first thing is it consists of 8-bit groups. See how these have the period there, and then there's 8 numbers? That's how you get the 127 dot whatever. So it's important to know these are broken into 8-bit groups, because you can save yourself a lot of trouble if you just break them up into small sections. Okay, and then they're ranging from 0 to 255. And that's just a math problem, because you'll see the octets, they can't go any higher than 255 unless you extend the amount of numbers we have which is where IPv6 comes in. Okay, so that's what it looks like. We know that, but we're going to talk about how do we get that. Now you can see the IPv format allows 4,294,967,296 unique addresses, and we ran out a long time ago. The IP address is divided into a host part and a network part, which we're going to talk about. The router, this is the router at your house that I was talking about, assigns you the host part. They assign you a host IP address, right? Or by an administrator, meaning you can have it pre-configured to assign it, whatever. The respective network admin assigns the network part. So the network admin figures out how it route or how the networks are going to talk to each other, but the host part is assigned by the router, or if the network admin sets it up beforehand, right? With DHCP and stuff like that. Okay, so in the past, further classifications took place here. So this is where you can actually see, you'll probably have heard of these, the classes A through E, different classified networks. You don't have to memorize this. I don't know that you can just look this up really quickly, but a class A, B, C, D, and E network. Class C is what you're going to see most of the time inside your home, those types of things. But they're all specified for specific things. There's certain ones you can see here, they're reserved, whatever. And they might be for emergency broadcasting or military or whatever. They're all reserved for very specific things. So that's why you can't assign those publicly. So you could assign these privately, but it's not best practice. But the reason I say that is because if you assign these publicly, it's not going to work, because that is reserved for a reason, right? You're not going to be able to get IANA, the person that owns all the IPs, to approve that. So don't build your network with the wrong class and then find out you can't use it. Okay, so now a further separation of these classes into small networks is done with the help of subnetting. Here's where we get into the bread and butter. This separation is done using net masks, which is as long as an IPv4 address. So that's where you see this subnet mask, where it's 255, 255, 255, whatever. As with classes, it's described with which bit positions within the IP address act as network part or host part. So what does any of this mean? I know you guys are probably sitting here going, okay, yeah, that's great. What does any of it mean? Well, let's get into it and see. Here's where we're starting to get into it. Here's the classes, right? A, B, C, D, E. And here is the subnet mask for each class. All right. Now you might say, this doesn't mean anything to you now. You're right, now. But this will mean something to you after you figure out how to do it. So you'll go, I'm not going to for you, but go back and check it out and you'll see what the difference is. Okay, so the two additional IPs added in the IPs column are reserved for the so-called network address and broadcast. So what you're going to see is that 255 number. That 255 number is actually higher than that, but only 255 are routable. So what you'll see here is they have the network address and broadcast address. So every time you plan a network, let's say you need 8 hosts. Don't plan it for exactly 8, because you need the network address and the broadcast address. The network address is how people are going to communicate with that subnet. So when a packet comes in, it has to have an address to go to that's not a direct host, right? It has to have one that the network can then send to the host. And then it has to have a broadcast address. What if I want to send it to everybody on this network? I have to have that, right? So those are the two things. You're going to have those IPs, and you're going to see that most network people, when you're talking to them, they auto take them out, meaning like they won't even do the math with them in thought. So if you see someone say like, oh, well, I need this a /27 network because I need blah, blah, blah. Like, they're not even thinking about them. They already have them taken out. So just keep that in mind, that most networks are built with those already in mind. It's not even it's a forethought at this point. Okay, so it's important that you remember that it's common for the default gateway to be assigned. So this is where you're going to know which IPs is it. It's common. So when it says it's common, it says it here. This is not a technical requirement, but has become a de facto. I've actually never seen a network that doesn't do it this way. So not that they don't exist, but this is how they do them. It's common for the default gateway. So this is how you're going to actually route traffic to that network, to be assigned the first one. So this is going to be the first. I say first. Yes, it could be assigned the last, but typically the last assignable IP address is the broadcast. So just take that with what you will. You might run into others, but that's typically how it's done. The broadcast IP address task is connected to all devices in network, so you can broadcast. It's a network message that is transmitted to everyone on that network. Doesn't require a response. It's just going to push it all out to everybody. Okay, so this is the last IPv4 address that is used. So that's what I was saying. The last IPv4 address is used for the broadcast. Again, that's not, I will never say it's always that case, but that is what I've ever seen. I've never seen someone that would. I don't know why you would change it, because if that's what everyone's expecting, it makes sense. So now the binary system. So this right here is what we're going to use throughout this entire process. This is why I opened Notepad. I want to show you. Okay, so the binary system is a number system that uses only two different states, zeros, ones. That's it, right? Now, opposite the decimal system. Okay, an IPv4 address. By the way, this is kind of just ramp. This is the type of stuff. This is the type of stuff that Hack the Box does that I don't know why they do. They just put stuff in here that confuses people. Like, all you have to do is say it's binary. It represents two numbers, 0 and 1. But instead they're like, and it's opposite to the decimal system that's 0 through 9. Like, how does that help them understand? You're confusing people by adding extra stuff that doesn't value anybody. So that's why you see me skim and skip a lot of this stuff. An IPv4 address is divided into 4 octets. Okay, that's this. We've talked about that. 4 octets, 8 binaries each one. So you'll see, here's an example of what the first octet looks like. Okay, so this is 192. You might say, how do you get that number? Well, I'm going to show you, this is how I still network. This is still how I do it. So anybody that's like, oh, if you've networked long enough, you just memorize it. I don't care. I write it down. It's easier for me. So you have right here, this is why I wrote this down. So, okay, you want to say, how did you get this number 192 into that binary? Well, 192, and this is where you also get a calculator out, right? Does 192 go into 128? Or does 128, I'm sorry, go into 192? Sure does. So 192 minus 128. That's 64. So guess what? This would be a binary 1 because, yes, it goes into it. Now, 64, does 192 go, or does 192 minus 128 get 64? Does 64 go into 64? Sure does. Well, now we're at 0. So the rest of these will be 0. There you go. Guess what? There's your binary 192. It's that easy. Now, some of you might say, well, where do you get these numbers? How do you remember this? Well, it's easy. If you remember, there's 255 hosts in a subnet, right? 255 in the mask, right? You could have more, but I'm just saying that's typically what you're used to seeing, right? Well, what's 128 plus 128? It's 256, but remember I told you one of them's already taken out. So 255 is what they're actually counting. So if you can remember 256 or 255, take it in half, you get 128, right? The reason you don't add the 255 here is because everything would go into that, obviously, because it has to. So you'd say 128, cut it in half. 64, cut it in half. 32, cut it in half. 16, cut it in half. 8, cut it in half, cut it in half, cut it in half. All of these numbers are just divided by 2. And then there you go. Now you have 1, 2, 3, 4, 5, 6, 7, 8. You have your 8 binaries that are in each octet. And, you know, there's 4 octets, so there's 192. So we could, and we're going to, go through and say, okay, well, what about 168? Okay, so right now, this is what our binary IP address looks like. One, 2, 3, 4, 5, 6, 7, 8, right? So now we'll do 168. So 168 goes into 128, right? So 168 minus 128, that's 40, right? So we'll say 168. So that's a 1 because it does go into 128. Now does 40 go into 64? Nope. So that's a 0. Does 40 go into 32? Sure. Or does 32 go into 40? Sure does. 40 minus 32 is 8. So there, it's a 1 because it does go into 32. Does it go into 16? Does 8 go into 16? Nope. Does, and if you're wondering, whoops, here's my calculator. You can see I did the math. It is right here. 192 minus 128, or whoops, 168 minus 128 right there gives me 40. 40 minus 32 gives me 8. And we just keep going down the line. So now we have 8. So we said it goes into 128. It does not go into 64. What's left is the 40. 32 does go into it. That's the extra 1. 16 doesn't go in there. 8. Yep. And that's what's left. So we say 8. And then we go 4, 2, 1. There's your 168, right? So now let's do the next one. 168, 10 is the next one. Well, 10's easy, right? I'll just bring it over here and show you guys when I'm done, because it's kind of taking up the whole screen. So 10's easy, right? Does it go into in 128? 0 times. It does not, right? Let's see. Does 64 go into it? Nope. 32? Nope. 16? Nope. 8 does. And then does 4? Well, the remainder of 10 minus 8 is 2, so nope. Then it does there, and then it doesn't there. Okay, and then let's see. The last one is 39. So we know it's not going to go into 128. We know it's not going to go into 64. It will go into 32. And the 39 minus 32 is 7. So will it go into 16? Nope. Will it go into 8? Nope. Will it go into 4? Yes. And then 7 minus 4 is 3. So then 2, then 1. Boom. There is your binary IP address for this. Now you might say, why do I need to know that? Well, we'll show you. That's how you determine a lot of stuff with your network. But you can see they did it here for us, and they did it this way. 0 plus 0 plus 0 plus 8, you know. So they did addition, I do subtraction, same thing. They add them up, right? They said we added 128 plus 64. I took 192 minus 128. So same thing. I think the subtraction is a little easier than trying to figure out which one of these numbers add up to it. But that's how they get the numbers, right? And then that's how you get the binary values. So you can see here is, if you look, let's make sure we add up here. 1, 1. God dang it, I keep doing that. So we've got 1, 1, 0, 0. All zeros, right? Now they separate theirs into the 4, but really it's 8, 8, 8, 8. That's why you get 24. That's why you get like a /24 network. Okay, so you can see we have 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. Then you have, add in the second, 1, 0, 1, 0, 1, 0, 1, 0, and then you have 0, 0, 1, 0, 0, 1, 1, 1. So we did it correctly. We've got the exact same thing they did. Now that's how it's repeatable. It can just continue. You can do that all day long, right? So now you can see decimal to binary. Okay, so if the binary value is 1, 1, 1, 1, all ones, you just add them up, right? Whatever the binary is, so whatever this is, you just add them up. You just say 128 plus 64. That'll get you 192, right? That's the number. So you guys see why I say if you can write this down anywhere, like I can tell you when I've taken all my networking certs and stuff like that, the first thing I do when I walk in the test room is I write 128, 64, 32, 16, 8, because I can sit there and I can do the math all day long and figure this out, right? I just need to have that chart to help me out. It saves me a lot of time. So now you say, why does any of that matter? It's great that you can take decimal numbers and turn them into binary. That's great. Well, that's where you start to figure out the networking piece. So now we have a subnet mask. The subnet mask is going to tell us how many hosts or workstations or computers or whatever you want to call them can actually operate in those subnets. So when I say, hey, I want a subnet and I need 60 people to operate in it, and then I know how I'm going to break that down in a network. And that's what we're going to show here. So you can see here, this is a subnet mask, 255, 255, 255, 0. So you've seen, hopefully you guys have seen CIDR notation where they say like this, it's a /24 network. Well, this is a /24 network. You might say, how do you know that? Well, look, they're all ones until here. Well, there's 8 ones, 8 ones, 8 ones. What's 8 times 3 or 8 plus 8 plus 8? 24. So that's a /24 network. So the subnet mask of a /24 network would be 255, 255, 255. Where do we get that number? If these are all ones, add them up. This equals 255. So what we're going to do, I'm going to just show you, is let's do another subnet, right? So CIDR notation is just a way of representing what we're talking about, and that is how many hosts can be in that subnet. So here they have 24. Well, I'll tell you, if you ever have a /24 network, it's 255. It's that easy, right? You can get 255 hosts. It's that simple. So we're going to talk more about this. We're going to keep going. But now we're going to actually get into the nitty gritty of subnetting. So now we're going to break it down. Now we know how to convert binary to decimal. Hopefully you guys, if you have to, go back, rewind. I know this can get complex. It's one of those things, it doesn't always click for people until it clicks. And once it clicks, you'll have it. So now here's the network part, or the subnetting part, right? So here they gave us a /26 instead of a /24. Well, if we do the math here, let's do the math, right? /26, that means there's 26 ones in it. Well, we know if we go 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, that's 16. 1, 2, 3, 4, 5, 6, 7, 8. That is 24, right? Thank you. Okay. Okay, so that's 24, but we know we need 26. There's 2 more. That makes us 26, right? Now 1, 2, 3, 4, 5, 6. So this would be our subnet mask in binary because we know it's a /26, right? There's 26 ones. Well, we know that this all ones is 255, 255, 255. So right there, we got our first 3 octets of our subnet mask. We just need the last 2. Well, check it out. If you add these up, we just did it. What is it? 192. There's your subnet mask for a 26 network, 192. Now you might say, and there you go, you can look at it right there. Now, you might say, why does that matter? Well, that's going to determine, the subnet mask determines how many hosts you can get in here. So here's the host part, right? So how many hosts can we put in this network if this is the subnet mask? Well, here's the beautiful thing. See these? All those zeros? Let's add them up. What's 32 plus 16? And we'll do the math here. And by the way, you could, I know the answer, but I just want to show you the math. So 32 plus 16, right? 32 plus 16, that's these two, plus 8 plus 4 plus 2 plus 1, plus 8 plus 4 plus 2 plus 1. And guess what? It's, boom, 63. You might say, well, that doesn't make any sense, but it's actually going to be 64. Like I said, when you're doing networking, keep in mind those are already taken out for you. So the first one is always going to be the gateway. So you can see we can actually have 63 hosts there, meaning people on the network that we want to actually have working. So if I said I need 40 people to work and maybe 10 for expansion for later, I know I need to make a /26 network. So I know I need to get the subnet mask and the IP addresses. Guess what? We know that the IP addresses, there's 63 of them. So guess what? If there's 63 of them and you're starting here at 160 or whatever, I know where the IP addresses start and I need 63 of them. So if, let's say I was doing, just for example, 192.168 168.1.0. And that's a /26 network, right? Well, we just did the math, and that gives us 63 possible hosts. Okay, well, I know 192.168.1.1 through 63. I can use these, and I start signing these two IP addresses to people. And guess what? Only those people, if I program this on a switch, only those people in a router can talk to each other. And that's how I know how many they have. And I have their subnet mask right here, so they know they're in that subnet. So that is how you actually do the math on it, and that's how you figure out how many hosts you need. So if I have a company of 200 people, and I say I need an HR department, I need a whatever, department, I don't know, legal department, a, whatever, sales department, whatever, right? And I know that, I know how I can start breaking down their subnets, because I don't want them to all have access to the same thing. So separation of network and host parts, that's what we just talked about here. So you can see the subnet mask determines where the separation occurs. So again, that's where the subnet mask comes in. You can see the subnet mask determines where does that separation occur. And you can look, this is /26. So it occurs right here on this 26th bit, right? The 26 binary. If it occurs way back here, look how many hosts you can get. You can get a ton of hosts, right? So that's where you start getting into large scale networking. That's a whole different ball game for network engineers. So now that's where the separation occurs, meaning that is where you're going to start seeing a lot of difference in the subnet mask is going to actually determine what hosts are able to be connected. What I mean by that is, if you had a host with this binary or something, it can't connect to that subnet. It doesn't make sense. It can't work. Won't work. It just won't route. It doesn't make sense. The math doesn't add up. It has to math, right? So now, if we now set all the bits to 0 on the host part, which we just did, we get the respective subnet's network address. So what they're saying is, take the IP they gave us, set all the hosts to 0, and do the /26. Doesn't really matter. If you go through here, that is what. So take all this and make it your subnet, or I'm sorry, not your subnet, your IP. Make these all 0. This is your network address. So right here, that's your network address. So for the example we used, right here, .0, if we actually went through, and there's nothing to go through here, but we would do all the binary for 192.168.1, right? And then this 0, we would turn all the bits 0, like we already did that on one of them, right? Then that would be your network address. So you can see it's an easy way to figure out your network address. The other reason this is so important, especially when you're talking about pen testing and stuff like that, is if you get on and you get on a machine, how do I know who I can talk to? Well, if I can see the subnet mask, which you can, right? I know how big the network I'm on is. So I can start to see how this scales, right? So you can start to see where the segregation happens, right? It's not normal for a IP address to start at 192.168.12.128. That would be weird if you're like, you just randomly chose 128. There's probably some IPs before that may be on a different network, and now I know it exists, right? The broadcast address, again, that's going to be the last one typically. So you can see the subnet mask is 192, so the last IP is 191. That's what they're going to actually use as a broadcast IP. So that means they can broadcast to everybody. So the way they did that, if you look, is instead of making these all 0s like they did on the first one, they turn them all to 1s, because that'll give you the last one, the last option. So they just added them all up basically, right? So since we know that the IPv4 address 128 and 191 are assigned, because we got 128 from making them all 0s, and we got 191 for them all being assigned, we know that there is, drum roll please, 64 network addresses. And you notice it says -2. That's for the network and the broadcasting. Keep that in mind. Now, the way I do it with this, you will have to take 1 away. Keep in mind, the way I do it with this number it'll almost always give you, like for 64, it gives me 63. So keep in mind, you'll always have to take that extra one away for the broadcast or the network, whichever one you want to call it. But this will account for one of them. It'll account for the network, but it will not account for the broadcast. So keep that in mind when you're doing the actual IP conversion, not the subnet mask. The subnet mask will be accurate. Okay, so now we have subnetting in a smaller network. So now they're taking it even smaller. So let's say instead of 64, we want to get it even smaller, right? So let us assume that we as the administrators have been given the task of adding in 4 additional subnets into the same 64 hosts that we already had. So keep that in mind. That's what they're talking about. So we can divide the 64 hosts by 4. So what they're saying is, how many can it divide by, right? Well, 64 can divide by a lot, but they're saying they're going to divide it by 4 because 64 split evenly divided by 4 equals, and you can look and do the math, 16. So if we have 16 hosts, there's your 4, right? What that means is the 4 is equal to this, right? So we find out the number of bits for the subnet mask, which we have to extend it. Okay, so what they're saying is we want 4 more subnets. Well, we need to figure out what kind of network we need. You could just do the math, right? You could just take 64 divided by 4, or not divided by 4, but divided, and figure out what's the equal amounts that you can subscribe to, whatever. But what they're saying is, okay, we have this 26. We know we need to split them into 4. Well, what's 64 divided by 4? It's 16, right? So we can take this 4 subnets here, right? See, that's what they're just giving you a chart that says 4. Now you might say, what does that 4 mean? It means we're going to go here and we're going to expand our subnet because we know we need 4 additional subnets, right? So if we need 4 additional subnets right here, we need to add 2 numbers. So if we needed 8 additional subnets, we'd add 3 numbers, blah, 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 etc. So we need 4 additional subnets. So we need to add 2 numbers to this, the 26. So now it's a 28 network. You might say, well, how does that help me? Well, remember our chart. If we can remember this, we can do it all. Don't forget that. So I'll show you. Here, this is a 26 network, right? We'll go like that. We'll add 2 more. Now it's not a 26 network. Now it's a 28. So if we do the math here, 1, 1, 1, 1, that's 128. Plus 64 plus 32 plus 16. So that actually equals 240, right? So now 240 is the subnet mask because we added those 2 additional. So that splits it up into 4 different networks. So that allows us to actually split them, and now they can only connect 8 hosts each one rather than the actual and you can see there it is, 240. And you can see this tells you how many hosts you can connect. If you add those up, you get the 8, or the 16, I'm sorry, I said 8. You get the 16. So you add those up and you get 16, and that's how you're getting these numbers. That's how you're figuring out how many hosts are allowed to connect, how many subnets I need to break it into, all that stuff. So you might say, okay, this seems a little bit confusing. Go back, reread it, try and walk through it, and then when we get to the example problems, you'll see kind of what I'm talking about. Now, the subnet here, they're just saying, okay, here's the first network that we are on is 128. So the first host that's available is 129, and the last host is 142 because the 143 is going to be taken here. And they're showing you that each one is the first and the last host that's able to be done for each of the subnets we just broke out. Now, mental subnetting, this is what I was doing before when I was showing you guys, is first octet, second octet, third octet, fourth octet. So if I know that the octets are just 8 bytes, so 1, 2, 3, 4, that's total. 8 times 4 is 32, right? So we know the first 3 is 24. So if I ever see a /25 network or something, I know it's in this last octet right here. If I see a /18, guess what? I know this is 816. I know it's in the third octet, right? So it's mental subnetting, meaning you're just quick referencing yourself in your head that you know where it's going to be. so you can start to quickly at least get an idea for it. Now you could do some, especially network engineers that have been doing it a long time, can probably do a lot of the stuff in their head because they've done it so many times. I'm not that good at math, so that's one of the reasons I don't do it in my head all the time. But you can see here, the next part, this is just what they're saying. You can use the modulo operation. It's heavily utilizing cryptology, blah, blah, blah. See, like, why is that important in here? They're just wasting your time. Given our previous example of /25, 25% 8 would be 1. You might say, what are they talking about? Well, 8 goes into 25 3 times, which is true, right? It goes in there 24. So you'll see, where's it at? 8. So it goes in there 3 times, 24, and the remainder is 1, right? So there's 1 left over, which is the network bit reserved for the network mask. So what they're saying is, if you wanted the 25 network, just look at the operator, the modulo operation, which is left over 1. What up? You might say, what are you talking about? Well, look at it. Okay. So if we want a /25 network, this is just basic. They're doing it quickly, and this is what I already did. It's just I didn't break it down this way. If I wanted a /25 network, if I do 8 in there, because again, they're 8 octets, the octets are in 8 bits, I know I'm going to get 24. The remainder is 1. There's your 25th. So I'll show you what I mean. So if I just quickly, someone asked me for a /25 network, quickly, I could say, okay, 24 goes in there 3 times, so that's knocks these 3 out. The remainder is 1, so there's, get rid of these, those will be zeros. That's a /24 net or 25 network right there, subnet mask. I could do that in my head almost instantly. That's what they're saying. They're saying if you can do it very quickly, that's how you can do it. All right, so now submit the decimal representation of the subnet mask following this range. Okay, so decimal representation, let me pull up my notepad here again. Okay, so submit the decimal representation of the subnet mask following the CIDR. Okay, so let's get rid of all this. And let's do 10, 200, 20, oops, 0, 27. Okay, so they're saying submit they want the subnet is what they're saying, right? But they're saying they want it in decimal notation. Well, that's easy because look, it's a /27 network. We just talked about that. Well, we know we can do it in our head very quickly. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then we know that's 24, so we need 3 more. 1, 2, 3, right? So now add them up. 128, 64, and 32. 128 plus 64 plus 32. That gets you 224. These are going to be zeros. 1, 2, 3, 4, 5. So now the actual subnet mask would be 255, 255, 255, and then we just did the math on this, 224. There's your subnet mask, right? It's that easy. We knew it was a /27. We get the we add up the binary bits, and as long as we can pull up that chart, we are good to go. Okay, submit the broadcast address of the following CIDR notation. So now we need the broadcast address. Well, all we got to do, pull this back up. So 10, 200, 20, and then 0. Now you might say, how are you getting the broadcast address from that, right? Well, there's a couple ways. You could just do the math. You could just break down how many hosts are in each one of these. But if you look, they gave you a little cheat sheet up here. We'll go up to it. Broadcast address. They're saying add 1s to all of the octets. Okay. So take all these and add 1s, right? So we've got 5 1s. So we have 1 plus 2 plus 4 plus 8 plus 16. Well, guess what? That equals 31. So you add that up, it equals 31. Guess what? There's your broadcast address. because you go 10, 220, 31. That is your broadcast address. If that doesn't make sense to you guys, what they're saying is this is how many hosts, how many total people can communicate on that subnet. You're taking the highest IP, and you're doing that by adding all ones here, and you're making that your broadcast IP. Now, it says split the subnet into 4 subnets and submit the network address of the 3rd subnet. Okay, so that should be easy because we've already split it up once, right? So total, we know that we have 32, right? Give or take. So let's get rid of this. So we go back up here and we look. All right, we needed to split it into, how many did we say? 4. Okay, so we need to split 32 into 4. Well, just do the basic math. That's 8, right? But if you go over here, we know we need 4. Look at that. You got to move the exponent 2 over. So what's that mean to us? It means we got to make this. We got to take 1, 2 right there. So now it's not 224 anymore. It is 224. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's 224 plus 16 plus 8. Okay, and that's 248. That's what network we're going to be breaking it into, basically, that's the subnet mask for the network we're going to be breaking it into, basically. But we know we need to do 8, right? Because we know the last one had 32. 32 divided by 8 is 4. So there, that tells us right there. We're just going to go 8, 8, 8, 8, right? So you might say, well, 8, 8, 8, 8 doesn't add up to 15. That's true. But guess what? Remember, we got to take away 2 of them. So if you go back here and we split these into 3, so we had 0 through 32, right? Well, we got to split them into 4 subnets. So we go 0 through 7, right? And then we go 8 through 15. And then we go, whoops, 16 through whatever. I'm not going to do the whole math, but it's actually 0 through 7, whatever. Split them into 8s. So the point is you're going to lose 2 of them, right? So 0 through, you lose the broadcast and the network. Remember that. So 0 through 6, 7 through, what is it, 14 or whatever. And then the broadcast address. Oh, I'm sorry. No, I had it right. It was the broadcast address. I was, for some reason I got confused and thought they were saying the network address. So it's 0 through 7 because guess what? Technically that 0 is routable. And then 8 through 15. So your broadcast address is always your last one. There you go. It's the broadcast address for the second subnet. There's your broadcast address. So hopefully that makes sense to you guys, because go back and do them if you have to. But the broadcast address, all we did was we split this /27 into 4 networks. And if you remember, all you do to do that is add 2 additional decimals. And when you do that, you're getting the subnet mask. But you can do basic math on this one, and it's just 8, 8, 8, 8, 8. So let's go ahead and mark that as complete and keep moving. Now, this is where there's not a whole lot here to talk about. They're talking about MAC addresses. They say it's a 48-bit 6 octet, meaning 8, 8, 8, 8, 8, 8, 6 times, right? Represented in hexadecimal. Hexadecimal is very simple. It's the same as binary, except for slightly different, and I'll show you what I mean. So now you can see here's the binary of this hexadecimal. Well, they're trying to break down MAC addresses to show you the layout of MAC addresses here first. So I don't know why they did it, but they kind of did it backwards. They'll show you in the next one what the hexadecimal looks like, but they'll show you in the next this IPv6 addresses. So we'll talk about that, but we'll talk about this first. So the MAC address is a total of 6 bytes. The first half, these first three hexadecimal bytes are organizational unique identifiers. What that means is they are actually assigned by IEEE. This means if you have a Dell whatever, they will know that because it is assigned to it, right? And then the second piece is the individual host. So it might be like, if you're reading this like a book, right? Dell hardware serial number 72, whatever. That's obviously a generalization, but that's kind of the thought, right? Is these first 3 are the manufacturer, and these next 3 are the unique identifier on that machine. So you might, every Dell computer, whatever, might have this same identifier, the first 3. Now, the reason this is important is if a host with the IP target is located in the same subnet, delivery is made directly to the target's physical address, MAC address. So if you don't know, a lot of switches actually do MAC address resolution. They don't do IPs, meaning they're not going to take the destination and the source and send it. They're going to get the destination, and they're going to look at what MAC address is assigned to that port, and they're going to send it off that way. So that's where ARP comes in. So if you guys have not heard of ARP, we're going to talk about it here in a second. So the other thing is with these MAC addresses, as with IP, there are certain reserved areas. So this first one is reserved. So you can see it's reserved for unicast and multicast. So what that means is 0 is unicast, E is multicast. So 0, the last bit identifies blah blah. It will be unicast means it's sent to one host. So that's it. It's sent to one host. That's the very last byte here, right? And then multicast. Multicast means it's sent to everybody, and then whatever host responds is the correct one, right? Theoretically, that can be taken advantage of, obviously. But so now you might say example is the ARP and DHCP. So what that means is ARP is actually a address resolution protocol. I thought they talked about it, but maybe I missed it. Okay, they do talk about it. I'll wait until they talk about it. Sorry about that. Okay, so now the defined values of each octet are marked in green. So what that means is this is what the MAC address multicasting looks like. This is a broadcast. So a broadcast is all ones, FFFFFFF. That means it's going to everybody, right? You're broadcasting it to everybody. So you can see the multicast address is a unique address, just like broadcast, which has fixed. Broadcast and network representation, a broadcasted call where data packets are transmitted simultaneously from one point to all members. So you're broadcasting it to everybody, right? So keep that in mind if you're ever doing any addressing. That can come in handy, and it can also be a bad thing, right? So now here you go. This is the global OU and then locally administered. So this is another one that's being reserved, meaning the MAC address has to have this. So what it is locally or administered MAC addresses globally. So again, if it's Dell or whatever, they will have a global one that's already been identified and defined by IEEE. But a locally administered one means like you're just making something or you're changing it or whatever. So that's how you can tell if it's a like stamped hard MAC address that the actual company put on there, or if it's one that you just put on there, made up or spoofed or whatever. So now you can see MAC addresses can be changed and manipulated and spoofed. So this is why you got to be careful. These are some of the attacks that happen with MAC addresses. MAC addresses, device, MAC spoofing, self-explanatory. I pretend I put my MAC address as yours. I change mine to make it look like yours, and then the network lets me in because they think I'm you, right? MAC flooding. This involves sending many packets to the MAC table, the address table, and trying to basically overflow the table nonstop so it doesn't know how to function and it can't work. Then you have MAC address filtering. So some networks configured only to allow access to certain MAC addresses, right? We could spoof our MAC address, similar to the spoofing one, and then actually get on your network. Now, ARP. This is where ARP is kind of like DNS. If you guys know what DNS is, if not, I'm not going to confuse you. ARP assigns the MAC address to the IP address. It correlates them. So when you get on network, you get an IP address. It knows that IP address is assigned to this MAC address. That's it. That's as simple as it needs to be, right? Don't get crazy with it. Now, here's what an ARP looks like. An ARP request looks like. So somebody comes in and they say, hey, I'm looking for who has the IP address of 10.129.12.101. Why would they look for that? Because like I said, at a routing level, they're sending it to the MAC addresses on switches. So they need to know what MAC address to send this to. So they say, hey, ARP, who has this IP? And then ARP comes back and it says, tell 10.29.12.100, tell that person who has this IP. Well, they came back and they said, this is their MAC address for the IP you requested. So you can see very quickly what an ARP spoof looks like. I can say, if they send a request like this, who has this IP? I can send anything I want to it. And if I can get there first and say, this is me, I'm in, I'm them, blah, blah, then you guessed it. Now they think I'm them. So you can do ARP cache poisoning, where I'm actually putting entries into the ARP cache so that it's responding with, hey, this person is that IP address, even though I'm not, and things like that. So you can see EtherCap and Kenable, they send falsified ARP messages. So again, they're just sending these messages so that when someone asks for whatever IP, it actually routes to you. So that's ARP spoofing and ARP poisoning. ARP poisoning is just man in the middle. They're sending all those and you can see IPsec or SSL that actually stops it. So let's keep it moving. All right, lastly, IPv6 addresses. So they don't go into a ton of detail here, but like I said at the beginning, IPv4 ran out very quickly. IPv6 is 128 bits long. So if you remember, the IPv4 is 32 bits. This is 128, so it's more than triple, right? So it identifies the host, the internet. IANA is responsible for signing IPv4 and IPv6. Okay, in the long term, IPv6 is supposed to completely replace IPv4, which is still predominantly used. But in principle, you can use them both, right? Okay, one thing to keep in mind here is this is a big difference. IPv6 follows end to end, meaning you don't have to assign your computer at home a special IP that's only local, and then it can send out to your router, and your router will send out a public IP. There's enough IPv6 addresses that they can say every end device will have its own IP address that can be sent out. That may sound really it's got its pros and cons, I'll say that. It would be nice so you don't have to do port forwarding and things like that, but there's stipulations, right? So here's some of the many features. You got larger address space, obviously. You've got address self-configuration, multiple IPv6 addresses per interface, so you could have an interface with multiple addresses, faster routing, end-to-end encryption, data packets up to 4 gigabytes, so the packages can be much bigger. You can see, here's the difference. Look at this, 4.3 billion for IPv4, 304 undecillion. I don't even know, or 340 undecillion. I don't even know what the hell that number is, but it's a lot, right? Okay, so you can see there are 4 different types of IPv4 addresses, or IPv6, I'm sorry. Unicast, anycast, multicast, and broadcast. Address for one single interface, anycast, multiple interfaces where only one of them receives the packet. Okay, so this might be something like you have a website, you need everybody to go to the website, but you're afraid it'll crash if it's just on one server. You might have everybody going to one website, but only one server is actually receiving it. That was a bad example, but just that's kind of an example. Addresses is for multiple interfaces where all receive the same packet. So, okay. So multiple interfaces where so you say, hey, anytime someone sends this, I need it to go to all these people. Okay. And then broadcast do not exist and is realized with multicast. Okay. So I don't know why they added that if it doesn't exist, but okay. Now here's where they explain the hexadecimal system. And I don't know why they didn't explain this the first time, but you can see it's actually way simpler. Okay. So you say hexadecimal 1 is 001. Hexadecimal 2 is 010. And if you look, they're following this exact same grid this is why I tell you just get this down. Okay. 0, 3 is 1 and 1. 2 and 1 put together equals 3. 4, guess what? 0, 1, 0. The difference is they get rid of this. They only do 8, 4, 2, and 1 because that's why there's only 4 bytes, right? So you might say, okay, well, that's great. But if you look, 8, 4, 2, and 1, once they get to 9, they stop and they go to A. A is just 10. So you just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. You might say, why'd they stop at 15 for hex? Add these up. 8, 4, 2, and 1, 15. It's as far as they can go. 1, 1, 1, 1, 1, 15. So hex is actually extremely easy. Just got to remember after 9, A, B, C, D, E, F. Right? That's it. Simple. Now, let's look at an example with an IPv4. Blah, 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 blah. We look at hexadecimal. So what they're saying is hexadecimal is written in, IPv6 is written in hexadecimal because it's so long that if you wrote it in binary, it's going to be, they want to make it easy for you. It'll be 128 bits if you wrote it in binary, right? So what they did is they said, okay, we're going to take this first octet in binary and we're going to make it hexadecimal. So C0. Now you might say, where'd you get the C? Well, look at C. 1100, 11 for 192.0.0. Okay. And then hex is broken down into 2 4 bits instead of 8. So C0. There you go. 192. And they just do it that way. Now you can see here's the full IPv6 address. Seems extremely long. But you notice all these zeros in here? 0, 0, 0, 0, 0, 0. Well, what they can do, and what they do is see how this just has 2 colons? That means those are all filled with zeros. They do that to save all that space, right? They're saying, hey, we're not going to make you just sit here and put all these zeros in here. Just put the 2 semicolons. We'll fill in the rest. So that's actually really nice. And then you have an IPv6 address consists of the network and the interface identifier. So the network part and the host part, just like before. The interface identifier is formed from the 48-bit MAC address. So we'll talk about that later. But they actually form it from the 48-bit MAC address, which is really nice. And is converted into a 64-bit address. In RFC5952, the aforementioned IPv6 address notation is defined. So this is what needs to happen for IPv6. All alphabetical characters are always written in lowercase, so it's case sensitive. All leading zeros of a block are always omitted. So if there's a leading 0, they're taking them out, right? 1 or more consecutive blocks of 4 zeros are shortened by 2 colons, what we just talked about. And the shortening of 2 colons may only be performed once, starting from the left. So the first one, that's it. You can't keep doing it. So this is IPv6. We're going to talk more about it, but hopefully this helped you guys. Hopefully you guys, I understand if you finish this and you go, I still don't understand what's going on. Go back, watch it again, and actually go back and do the examples. I get it. Networking was one of those things in my head when I was doing subnetting and stuff. It didn't make sense. I didn't fully get it. And then it clicked. And once it clicked, I got it. I fully understood it. So hopefully this helps you guys. I hopefully will eventually come out with my own networking class because I do think the way they teach this is very poorly done. So just let me know what you guys think, and let me know if you want me to continue this path or if this is the only piece you were interested in or what you guys' thoughts are on it. Thanks, guys.